Okay, I'm glad for that. We have to really think about what we mean by time complexity, all right? And I'm going to tell you some things now, and you're going to get all nervous, and it's really not hard, all right? All right, so running time depends on the time as a function of the size of the input, right? So you have the size of the input, and you map it to the running time, right? I think of size as being how much work it's for me to give you the input, right? So whenever you're in doubt, just say, how much work is it for me to give you the input compared to, or for you to read the input, compared to how much work it's for you to solve the problem, right? You know what I'm saying? All right. How much work is it for me to give you this value? I'm going to say work 5, right? I give you an 8, I give you a 3, right? Right? Do I hear a 9? Right? So here are various measures. I could talk the area of the paper, right? I could talk the number of bits to write it down as 17. I could talk about the number of digits as 5. I could talk about the value is 83,000, right? Everybody see that these are different ways I could measure this number, size. Which ones feel right to you? The context we're doing right here, which is how much work is it for me to give you the number? Right? This is kind of intuitive. This is the formal definition. This is within a constant, converting from the number of digits to the number of bits. You just multiply by 3.32 because that's the log of 2 base 10 or something, right? This one is different, right? These are all multiplicative of each other. This one is bigger, right? In fact, to get from the value to the number of bits, you take the log, right? To get from the number of bits to the value, you do an exponentiation, right? These are exponentially different from each other, right? Does that make sense? Everybody get this? Right? So let's just do here, anybody who doesn't get it, let's do a really simple game here. I'm going to read a number out, and then all you have to do is count 1, 2, 3, 4 until you get to the number. All right? So I'm going to say 83920. How long did it take for me to give you the number? Right? Nothing. How long is it going to take you to count? Exponentially bigger. Right? The value is exponentially bigger. All right. So let's go back to which is faster. Right? How big is my input here? Well, maybe it's 2n because I have, right? But it's order n, right? And the running time, right, is square of that, which is 400, right? What about here? The value is this. So the value, the time is that, right? But the value is exponential in the number of digits, right? So in terms of n, this algorithm is in square. In terms of the number of digits, if n is the number of digits, then this algorithm is n squared, and this algorithm is exponential in n. And it's either 2 or 10 base, depending on whether these are bits or digits, and I don't care. Right? Everybody buy that? So I call this kindergarten algorithm an exponential time algorithm. And that is why it's lousy. Right? Does that make sense? Right? All right, you add a number of digits, and the running time goes up by a factor of 10.